Sporadic E or ES is a fascinating and often unpredictable form of radio propagation that occurs in the ionosphere's E region, roughly 90 to 160 km above the Earth's surface. Unlike the regular E layer, which is predictable based on solar radiation, sporadic E consists of thin, dense clouds of intense ionization. The exact cause of sporadic E is still a subject of research, but the leading theory involves wind shear. High altitude atmospheric winds moving in opposite directions create a squeeze effect on metallic ions left behind by burning meteors, concentrating them into thin, highly conductive layers. These ionized clouds move horizontally at speeds up to 400 km per hour, causing signals to appear and vanish unexpectedly, hence sporadic. Metallic ions. Unlike the oxygen and nitrogen ions that drive normal propagation, the metallic ions, magnesium ion, in ES clouds recombine very slowly, allowing the layer to persist even after sunset. Intensity. These clouds can become so dense that they reflect radio waves that would normally pass straight through into space, particularly on VHF, 30 to 300 MHz spectrum. Sporadic E is famous for creating short skip conditions that can make low power stations sound like they are in the next room. A single hop typically covers 500 to 2500 km. Under extreme conditions, double hop propagation can occur spanning over 5000 km. Because the E layer is lower than the F layer, there is less signal attenuation. This results in incredibly strong, stable signals, often referred to as armchair copy. It most commonly affects the 10 meter 28 MHz and 6 meter 50 MHz bands. During intense openings, it can reach the 2 meter 144 MHz band and even the FM broadcast band 88 to 108 MHz. If a single hop of sporadic E is like a lucky bounce off a mirror, a double hop is like a world-class trick shot. It allows radio signals to travel much further, often over 4000 kilometers, by using the Earth itself as a middleman. In the first bounce, the signal leaves the transmitter and hits a dense cloud of ionized gas, sporadic E, in the upper atmosphere. Instead of passing through, it is reflected back down towards the Earth, just like a standard single hop. Next step is the ground reflection. This is where the magic happens. Instead of hitting a receiver, the signal hits the surface of the Earth, ideally the ocean, which acts like a giant conductive mirror. Though solid ground works too, the signal bounces off the Earth's surface and heads back up into the sky. To complete the double hop, there must be a second sporadic E cloud waiting at just the right spot. The signal hits this second cloud and is reflected back down to Earth a second time. Double hops are much harder to achieve than single hops for a few reasons. Alignment. You need two separate patches of magic clouds to appear at exactly the right distance from each other. Signal loss. Every time the signal bounces off a cloud or the ground, it loses some strength. The signal has to be very strong to survive 3 reflections and still be readable. Geometry. The takeoff angle of the radio wave must be very low to cover that much distance. While a single hop might let you hear a station from 1000 miles away, a double hop can bridge entire continents or oceans on frequencies like the 6 meter that are usually restricted to local line of sight distances. That's a real super DX. While the name suggests randomness, there are clear patterns to when these openings occur. Primary season is late May to August in the northern hemisphere summer. Secondary season, a shorter, less intense peak during the winter solstice, December-January. Time of day usually peaks in the mid-morning and again in the early evening. Solar cycle. Interestingly, sporadic E is largely independent of the 11-year sunspot cycle. Impact on radio services. Amateur radio. The 6-meter band is nicknamed the magic band precisely because of sporadic E. A band that is normally dead can suddenly open up to transcontinental communication for a few hours. FM and TV. In the days of analog television, sporadic E was responsible for co-channel interference, where a viewer in New York might suddenly see a broadcast from Florida overriding their local station. Digital modes. Modern modes like FT8 have made it much easier to detect sporadic key openings that are too weak or brief for voice, that is SSB or CW.